First off, we have Dr. Giovanni Grasselli from the University of Toronto to tell us about rock fabrics. Giovanni.
Thank you. Thanks a lot for the opportunity and this amazing event and giving us the opportunity to be in the Netherlands. And so let's see. So today, what I'm going to talk about is start from what I presented last year. I will summarize a little bit the experiments and the results that were presented last year, and then I will expand on how we can actually use what we learn in the lab and apply that to the field. But before starting, I really would like to stress on the fact that this is not my work, it's the work of an amazing team, and we contribution for many current and past students and postdocs and associate and collaborators on this presentation. So, but as a really field of study, we're going to focus on the mountain formation that is really on the Western Canada Sedimentary Basin. Is one of the major unconventional play in the world, and what we can notice when we look at the development of the mountain is that really the completion practice are guided by the principal stress orientation that is measured in that area. So, when we look at drilling and production, and we design our wells, and we think about how the fracture will develop, we really look at, we assume that the fracture will develop along a path that is dictated by the principal stresses. In particular, the fracture will open against sigma 3, the minimum principal stress. However, when you look at the model that are used, this is not enough. You need to include, in order to match the production curves, you need to include something else, and generally that something else is looking at the presence of natural fractures that will enhance the production and allow you to match what is observed really in the field. And there are several different ways that you can include those in the model. Now, when you look a little bit back and you go in 1957 was the first paper by Hubbard and Wills that really found or postulated or through experiments that when you hydraulic fracture a material, that material will split in a direction that is function of the principal stress, and they will open against sigma 3. And what they did a very nice and intriguing experiments. They used gelatin and did the plaster of Paris so they could see the fracture developing, and consistently they saw that the fracture will opening in this homogeneous medium against the sigma 3 directions. But one sample was actually done with stratified gelatin that has these weak interfaces, and that fracture was not exactly the same as the others. And in their discussion, they discount that because of the presence of those interfaces. So that made us to start thinking, well, any unconventional play is actually deposited anywhere in the world in the same environment. It's a low energy depositional environment. So they all have bedding planes, these weak interfaces. And the question we had is, can we make something out of these weak interfaces and use them for better develop the fields and better understand how the fracture develop? So, and that's a big question. Can we replace the concept of natural fracture with something else that might be bedding planes? So to answer this question, we decided to replicate, if you wish, the experiments by Hubbard, but in a very different laboratory setting. We took advantage of a polyaxial machine. That is, polyaxial means that it allows us to test the cubical samples, and on each direction we can apply the principal stress we think that rock will experience. And we did that on cubes that were recovered both from the reservoirs and outcrops of mountain formation. So what we did, we really replicate a single stage open hole completion by injecting at the center of our cube once that was stressed in the according to the stress field that or values that were estimated at the reservoir depth in the mountain. And by doing that, we could really reproduce all the stages that are normally measured during hydraulic fracturing. The key is also that we were able to instrument our vessel by a lot of different sensors, and specifically we could look at the deformation, but also the acoustic emission that is a proxy in the lab for microseismicity. So we could really listen how the rock was cracking during the experiments. And at the end, this was what I presented last year. We were able to see what the fracture, how the fracture developed, how our stimulated rock volume developed, and actually that has quite a bit of similarities with the discounted experiments that was present in 1957 paper, where the interfaces actually had a role. Now, when you look a little bit more in depth to the results, what you can see is the bi-wing fracs are really a minimum percentage of the fractures that were activated and developed in our cube. And about 60% of those fractures are actually bedding planes that are completely discounted in the models up to date. And when you look at the aperture, actually those bedding planes were a little bit more open than even the hydraulic fractures. And many of you knows that the transmissivity of a fracture depends on the cube of the aperture. So if they were more open, they were actually contributing more to the flow and the production of those areas. Now, when you look at really the real geometry and you zoom into the rock, you can start seeing, and these are real results mapped out of one of our experiments. You can start seeing an echelon fractures, Horst and Grab activation in our samples. But an echelon fracture are also proxy for shear. So the cube not only open along the bedding planes, but there's an indication for some shear displacement along those bedding planes. So that's quite interesting. So at the end, we try to think what was the reason for actually opening against the bedding planes that, by the way, were not against sigma 3, were opening against sigma 2. And the key is, in our opinion, is sort of obvious. The material strength of these shale, mudstone, siltstones are really not isotropic. You have a transversely isotropic material with a direction that is weaker than the other one. So it splits easier along the bedding plane. So you can really open them. So when you account also for the tensile strength of the material, and that change in tensile strength along the different directions, we actually get quite a reasonable results, and mathematically for sure is going to open against these bedding planes and not against sigma 3. And that really help us to explain in a simple way why our results were not what we were expecting at the beginning. Now, that means that our rock is actually very heterogeneous, and depending where you're loading with respect to your bedding planes, the strength of that material will change. Now, what you are seeing here, and it will be important, the story I'm going to tell you later, is our results out of digital image correlation measurements. And what you can see is, what is it? Oops, okay. So you can see different colors, and those colors are correspondent to the strain field that is developing during a uniaxial compressive test on the rocks that are tested at different orientation with respect to the bedding planes. But what is key is that what you need to retain is that the contrast in color means that it's a contrast in the formation. That is a proxy for a contrast in stiffness in the material. So you have some material where some part of the rock will deform more, and some other that will deform less. And that is going to create stresses within the material that are not exactly where you might want to think or you were considering. So overall, all these laboratory tests brought us to basically a few important considerations. One is that actually the strength of the material and the transversal anisotropic character of our material is very important. And a few other points that I'm not going to touch, but it's just for you if ever you're more interested. Now, what is really the value out of this research, we think? Well, we think that clearly the value is that we need to consider the bedding planes. And by maybe engineering our completion, by taking advantage of the bedding planes, we can add value to our completion. But the other part, that is what we're going to talk today, is that can help to avoid value erosion of our fields. Value erosion generally is associated with seismic events that are associated with completion. And now I'm talking about oil and gas. But in Switzerland, there are examples of geothermal projects that have been killed by inducing seismic event, Basel and St. Gallen, for example. In South Korea, same. So actually, when you fracture and you geoengineer in your subsurface, you might create seismicity. And now it's important to understand why and how to manage this risk. And I think that our results can help a little bit on better understanding. Now, let's go back. I was telling you that we were able to, we instrumented our cube and we could listen at the rock. And you saw that the rock was really fractured, a lot of fractures. Well, when you look at the data that were recorded for the acoustic emission, the microseismic proxy in the lab, well, we could find one event. Not much, not really much. That means that all the bedding planes were silent, were aseismic. No way to actually know if they were failing or not. But when they fail, and you see on the DIC, there will be some stress, some tensile and compressive stress that develop at those interfaces. That's interesting. So, and there are other studies, we're not the only one, that say that the bedding planes, they fail in a seismic way, so you can really listen them. So microseismicity can really help you. Now, let's go back to the Montany. Let's have a look at what we can access at the larger data. And both BC and Alberta, they make their data available. So you can go in this database and start looking at what is the microseismic and the seismic events that are associated with our development. There's a lot of data. And you know, a lot of data are difficult to treat, but you can start looking at some trend. Now, we're looking at the Montany, and what Thomas is presenting that in the poster, so if you're interested, you can ask more questions about the work. But what you see is that, what you notice that there are different type of seismicity. In particular, the depth of the seismicity depends on where you are. So the green area is a cluster of seismic event, induced seismicity, that is actually at the same level of the completion, about 2 to 3 kilometers. The yellow and blue actually are much deeper. So, and these are associated to two geological formations. One is a graben area in the green, makes sense. So this is where all the seismic events are located. The other one is close to the thrust belt, Cordillera thrust belt. So, and those events migrate really to the basement and create much larger events. Now, what we're going to do is to look at one specific area around the Cordillera thrust belt, and in particular to one well that triggered a 4.6 event. So that what I need to say is that generally the Montany is in between a strike slip and a reverse fault type of regime. And definitely on the thrust belt, it's more on, I would say, reverse faulting. Now, what we think, and we sort of develop as a conceptual model, is that you can think that the Montany formation is a lower stiffness material that is sandwiched between higher stiffness, the basement, and the formation above. And because of that contrast in stiffness, and the thrust belt that is actually keep on moving, what is happening is that you will develop some sort of induced tensile and shear stresses at the interface in between the formation and within the Montany basically at the interface of every layer. So, and what you can is also think about that these bedding planes are weak and they can part very easily. So, and we think that you might be able to lubricate a fault by just injecting fluid and fracking your rock, even at large distances. Why? For the simple reason that there are regional markers that are extensive planes that are very, very weak, that are completely connected in the entire region. And if you hit one of those are so easy to break that you might actually reach a formation, a fault, many kilometers away. And, well, that is sort of the hypothesis. And when you start looking at all the data and start looking at the literature, for example, Eaton's group also said that the proximity to the thrust belt is the most important predictor for seismogenical potential. Again, same idea, same concept. The other interesting part, because when you inject, and in the lab, we are opening against the bedding plane. So we had really a vertical displacement. There is INSAR as a satellite interferometry that allow us to see what is the displacement with time of the surface of our Earth. And when you look at INSAR data at the well during the injection, you could see actually an uplift. And the uplift is actually quite large. And quite large as extension, aerial extension, also about 2 centimeters uplift on a couple of kilometers diameter, a little bit more. So definitely you were opening bedding planes during that completion. Now, and we think that that is what really help in triggering the earthquake that was recorded. So we really think that the bedding plane might play a big role, not just in the production, but also in the potential for seismicity, and that should be accounted for. Now, of course, not the other way. So, and of course, the other big problem in those areas is actually casing deformation. There are definitely evidences for slippage of bedding planes that will actually will cause this casing deformation. Now, the question is it true that there are shear along bedding planes, this slippage? Well, when you look at the cores, you can find a lot of evidences for silicious surfaces on the fractures there. That those are again another evidence for shearing along those bedding planes. So now, So what? What are really the implications we think of this work that has been really carried on, mainly experimental in the lab and with support from the field data? Well, we think that, first of all, we need to characterize clearly the rock, its strength, and its anisotropy. So definitely we need to have a number, a strength that is associated with the bedding planes and with the intact rock. And this is going to be key if we want to model successfully hydraulic fracture operation, injection of any type of fluid, CO2, hydrogen, water disposal in underground, because of the formation. And by doing that, we can really improve our model. We can better estimate what is the stimulated rock volume. Now, and we can start modeling. And I go back and start again. Oops. It doesn't work anymore. So, it did. So, nope. Okay. Can you move in the next slide, please? Okay, thank you. If you look at the model, this is actually a 3D model that explicitly tries to reproduce the fracturing that is happening in the reservoir, and especially the development, the failure of this regional weak plane. And you can see that the fracture is developing, and as soon as the fluid hits that particular plane, extend almost in just a matter of few instants. So what you think is that by accounting for the bedding planes and this regional weak plane, we can explain a lot of unknown or unexplained, not fully explained phenomena in the in different reservoirs. So can you go next one? So with this one, I really want to thank Energy Simulation and all the sponsors that have made this work possible. And yeah, I'm ready for questions, if any. Thank you.
Thank you, Giovanni. Questions from the floor? Questions online? I guess people are watching or typing or still sleeping. Anyway, I have a question for you. So yes, bedding plane and departing of the bedding plane, potentially can dictate your fracturing and whatnot. So I guess you mentioned about not necessarily the minimum stress you have to overcome. So if it's a bedding plane, assuming it's horizontal, would it be just a vertical stress total stress you have to worry about?
Pretty much, yes.
Right.
Plus the strength of your material. So the key is when you break a material, you need to overcome the stress, but also the strength of the material. So the strength does not count if it's the same everywhere. For bedded formation, the strength of to part the bedding plane, so what is the stress you need to apply is much lower than across that.
So how would you establish the cohesion between the interface into the bedding plane? How do you
establish model?
Yeah, no, actually, do you collect core samples and measure that?
So what we did to get the numbers that we use in the models, and we provide for any models, doesn't matter, ours, yours, commercial, is we do test the samples in different directions with respect to the bedding. So we test them both in compression and in tension. So we fully characterize the material with respect to the orientation of loading. By doing that, you can really incorporate those information in any model.
Okay. You also mentioned that sometimes your microseismic measurements cannot detect that bedding plane parting. So if so, what other instrumentation or techniques you would need to actually establish or support the theory about bedding planes parting?
So underground, we need to rely on indirect measurements. Generally, historically, microseismic has been a proxy for propagation of fractures. But the fracturing process needs to irradiate enough energy to be detected by your sensor, by your geophones. So right now there's several different approaches, and I think you need to rely on a combination of them. So fiber optics, for example, they give you some indication, especially if because they can see the localization or aperture of a fracture if goes through the fiber optics area. In SAR, this is satellite survey will allow you to see what is really the movement and both horizontal then vertical that can be help with the GPS data to cover the time scale in between one satellite pass and the other that are several days. And the other thing that I think is very promising is also to have a better look at the pressure data that you are recording during your completion. And company, well, I mentioned that because not just because it's one of the sponsors, ShareFrac, but they are actually we're working very closely today with them to try to see how we can use the pressure response during injection as a proxy to understand what is the type of fractures that open, and by there you can still infer if there are bedding planes or more tensile vertical cracks. So I don't think there is one solution. It's a combination of methodologies that you can use to try to better understand what is happening at the well.
Okay. Dr. Chalatenik's got a question.
In case I missed it, Giovanni, because I'd seen the presentation in Banff.
Yeah.
There you chatted about it a bit, and I think I forgot to ask you this here. Do you see that we have to actually do sort of direct tension measurements to try and get a tensile measurement of the bedding planes, or does it have a tensile strength? Do you think that is right? Because Montney's pretty fine grained and all that kind of stuff. So, what do you foresee us having to do, perhaps, in trying to characterize that, like a direct tension or something, or what would we do?
So we are doing both direct tension and Brazilian. Brazilian is a direct tensile strength, and what actually in Banff, Patrice River show a very interesting way to explain what is the difference in strength in between what you measure during indirect tension and direct tension. It makes to me a lot of sense. So anyhow, yeah, we try to characterize both. In direct, it's more complicated because it's really a difficult type of test to do. There's a lot of nuances on what the data you are going to obtain, and for those that are interested are staying for the school, we're going to discuss about that, because testing, as Rick knows, are challenging, and to have good data is key, and but doing a lab test doesn't mean that you get a good data. So, but yeah, direct tension or indirect, both we're doing.
Okay, question there.
So this is Wendros Hao from Utrecht University. So in the experiment or the simulation, so when the fluid enters the fracture or the bedding plane, it slips. So does this mean the pore pressure or the stress related to the injection triggers the slip? So I mean, if the bedding plane or the fracture is very impermeable, so will it trigger any seismicity?
Well, let's put it in this way. There's a lot of assumption on what I'm going to say, and there's really my opinion. What we think, I personally think, is that in this particular case I'm discussing is a thrust fault regime, and GPS data shows that the crust is moving. So that thrust fault is already moving very gently. What I think happened was that in some way, and I removed those information, but on the microseismic data you could see other hints on fluid connectivity from the injection point and the fault. So what I think it happened was that you had that really direct conductivity that triggered the slip. And that would also explain one contrasting, if you want, results. When you look at the seismic events and you invert for that, it suggests that there is a natural earthquake. What we think it is sort of natural, but it's been triggered or accelerated by the operations. That is it's my interpretation looking at all the data together. So I'm not sure I answer your question, but
I think
Thank you.
that's fair enough. I guess it's time, 3 o'clock. There's a lot more follow-up in terms of reservoir characterization, rock and subsurface characterization, not to mention modeling to help the industry. So I appreciate the work. Thank you again.
thanks a lot for listening.